Hi, today I'm going to start to talk about the moment of force in two-dimensional domain. Before I start to talk about the moment, let's talk about a little bit about the concept of moment, and then I started to show you how to calculate the moment in 2D domain. So what's the moment? If we want to think about the moment, when we have any force that causes the rotation, we call that moment. For example, whenever we open the door, when we push the door rotates. So we apply a force on a door and then rotate about the hinge. So that rotation caused by the moment of our force, that the force that our hand put on the door, so it caused to rotate. When we grab the knob or the door handle and we rotate it, so we apply the force on that, and the force we apply on the door handle cause that rotate. So that's the moment cause that rotate. When we drive a car and we get the steering wheel, so when we apply force on that, it rotates, and that rotation caused by the moment that the force from our hand causes. So any rotation we have, most of the time when we have a rotation, the rotation comes from the moment that the force that the force caused that moment, and that moment caused the rotation. So for example, if I consider this marker and look at it, if I apply a force on that, it starts to rotate about the hinge here that I hold it in. So here I apply a force and it starts to rotate. My hand is the force is going downward, but the result, it also causes the moment, and the moment causes it to rotate about that fixed point. This is how we use the moment in many cases in daily life. How we calculate the domain, the moment. So assume we have the point O. We have the point O, and we have the force F. I want to see what moment or what rotation that force causes or create. So if we consider that forces and we consider the distance between that point and that force is d, then the moment, the magnitude of the moment created is going to be the magnitude of the force times the distance. Note that the distance here has the right angle with the force, so it's a normal to the force. So here the distance goes from the point and it's going to be normal to the force, and that's the magnitude of the force the magnitude of the moment we have from the force that has a distance of d from point O. So it's a moment about that point. About the direction. So this is the magnitude of that. So I want to find about the direction of that moment. We are going to use the right hand rule. So remember that if I if I put my four fingers and curl it in the direction of rotation, my thumb is show the direction of the moment, the moment vector, where it's going to be the direction of the moment vector. So if I assume here again the marker, if it is a marker, apply force on that and it rotates like this. So I put my forefinger curl it toward the direction of the rotation, then my thumb shows the direction of the moment or moment vector. So it's going to be in the z-axis. So if this is rotating in the x and y plane like that, then the moment would be perpendicular to that plane. So if it's rotating in the x and y, the moment would be in the z-axis. So one more time, we just we curl our forefinger in the direction of rotation, and the thumb shows the direction of the moment. If it rotates this direction, for example, it goes from here to here. So then the curl is this direction. I put my forefinger, and then the moment is going to be downward. This is how we find the direction of the moments. For here, we know that it rotates like that, and we put the curve like that, and then this the thumb, which is going to be out of the board, is the direction of the moment. One point that you may need to understand, to think of, that sometimes you may get confused that which direction is going to rotate. Always, probably the easiest way to assume is that assume a cord or a rope connected the point to the force. So assume I put a cord here and another end of the cord on the rope. Fix this end of the rope and see if you apply that force, which direction is going to rotate that rope. Is it going to bring it up or counterclockwise, or bring it down or clockwise? So most of the time, if you do that, it gives you the good idea of which direction that moment is going to rotate about that given point. So that's the magnitude, and that's the direction of the force that we have. Sometimes it might not be that obvious to find that distances. For example, assume that we have let me grab these and this, and assume, for example, for that point O, assume I have a point O, and then I have a force here. So it's not that if I connect the point O to the force, it's not going to be normal to that force, so that the angle is not going to be 90 degrees. In this case, as I said, the angle should always be 90 degrees, so it should be normal to the force. When we have this situation that we cannot directly connect the point to the force and get the normal line to that force, what we are doing is that we extend the line of action of the force. So we extend the line of action of the force, and then we draw that distance from the point to the line of action with the normal angle. So this is going to be the D. The same if the forces will be in any other location. For example, if I have a force here and I want to find the moment about the O, again, if I connect it from O to the force, that is not going to be the right angle. So what I do is just I draw or extend the line of action, and then I find a D that is normal to the line of action. So in short, if you can find a distance directly by connecting the point to the force and get that perpendicular line, perpendicular distance to the force, do that. If you cannot do that, extend the line of action of the force, and find the normal distance to the line of action. So either find the normal distance to the force, or find the normal distance to the line of action of the force. Remember that always that distance should be normal to the force. And the other point that I want to raise that is we have a couple of forces here. For example, assume this is F1, this is F2, and this is D1, and this is D2. When we are working with the moment in the 2D, we just use it in the scalar format, so we just add them or subtract them together. When we're working, if I want to find the resultant moment, I have to find the moment from each of these forces and then add them all together. To do that, what we need to know is that we have to find a positive, we have to know the positive and negative direction to find the standard positive or negative direction, and most of the time it is what you yourself decide about which direction of rotation you will consider as a positive. One way of that is that you say that, okay, I'm going to consider counterclockwise positive, so all the rotation is counterclockwise positive, and all the rotation are clockwise or negative, or the other way around. So assume here I want to find the resultant moment for F1 and F2 about point O. So the very first thing I'm going to do, I'm going to say, hey, I assume the counterclockwise rotation is positive. So it's going to be this direction, which is this direction of rotation, which is counterclockwise positive. And then I want to find the sigma m. So I find all the moment about the point O. So I start from the point F1. If I look at the F1 about point O, so again I said, assume I connect the point O to the force with a rope or with a cord, and then fix this end and let that force pull that rope. So if I have a rope here and let the force pull it, it's gonna rotate this direction. It goes that way, which is gonna be the clockwise. So it's gonna rotate clockwise. And I said counterclockwise is positive. So the moment created by force F1 about point 8, because it's rotating clockwise and we consider counterclockwise as a positive, so it's going to be negative. So it's going to be negative F1D. Then we come to the F2, and again assume consider end of the force with the rope to the point O. Fix the point O, and let's see how that F2 rotate the point, that rope. So if I connect it like that and let it fix the point here and let it rotate, so it's gonna push the rope this direction, or in other words, rotate it in this direction. So it's gonna rotate it like that. So it's gonna rotate it in counterclockwise format. So it's gonna be positive because the we consider counterclockwise positive. So its sign is positive and its magnitude is F2, so D1, so it's F2 D2. So this is going to be how we are going to add them in 2D or scalar format for the moment. So remember, just assume a positive direction, like here I chose counterclockwise, and then add them all the moment together based on the rotation direction. So for example, here we add, if you have more forces, we add all the counterclockwise moment together, and then we subtract all the clockwise moment from those that are counterclockwise. So counterclockwise is going to be positive, and clockwise is going to be negative, and just add them all together. Simple add and subtract. Now let's look at a couple of simple example, see how we can do that. So assume I have a element here, so it's going to be like that. So I have an element here. It's going to be 2 meters. And I have a force of 100 Newton apply on that, and I want to find that the moment of that force about point O. So when I go there and look at that, it says, okay, first of all, I have to choose the positive direction of rotation. So again, it says that the positive is counterclockwise. So I assume the counterclockwise is a positive. So the M is force times distance. And look at that. If I look at that and I look at here, it says, okay, if I connect the rope from O to the force and let it rotate it, it's going to rotate it this direction. If I fix that rope here, it's going to rotate it this direction. So it's going to be clockwise. Because it's clockwise, it's going to be negative, because it's the opposite of the direction we chose. So it's going to be negative sign. And then the force, which is going to be 100. So the force is 100 Newton times D. And the distance is the normal distance from the point to that force, and we know that, so that's the normal distance from the point to that point, which is here, is exactly 2 meters. So that's the distance D, that's the force. So it's going to be times 2, and it's going to give us minus 200 Newton meter. The moment of that. So is the negative, it means that it's the clockwise rotation, because we chose counterclockwise positive. So it's negative, so it should, the rotation is clockwise, and the magnitude is 200 Newton meter. So now let's make it, look at another simple example. So if I come here, and the same thing here, I have, assume I have 2 meter high. So it's a 2 meter. And then I extend it 1 meter in this direction. So it's a 2 meter. And then this is going to be 1 meter. This is point O, and this time I put 100 Newton here. I want to find the moment of that force about point O. So that was that. Again, we need to define the positive direction of rotation. So here is, I consider that this is the positive rotation direction. I look at that. So M about O is, so first I have to say is it positive or negative. Again, if I connect the rope from here to the end of that force, I connect the rope from the point O, which is here, connect the rope from here to the end of the rope, and see which direction is going to rotate it. If I connect it, so it tends to bring the rope down, so it's going to be clockwise rotation. So it's opposite of what we chose to be positive, so it's going to be negative. Then the magnitude of the force is 100, and then the distance is the normal distance to the force. So if I directly connect the line from O to the force, it's not going to be normal distance. When I cannot connect that, if I connect the line from here to the force, the angle between them is not going to be 90 degrees. So what we are doing is that in this case, as I told you, we extend the line of action of the force, and then we draw the normal distance to the line of action, which is going to be from here to here. So that's going to be D. So that's the normal distance from the point A to the line of action, because we can, if we draw it from here to here, it's not going to be normal. So it's going to be like that. So it's a normal, and if you look at it, so it's 1. So the distance is 1. So it's got the 100 Newton meter. Again, it's the negative, it means counter, it is clockwise rotation, and the magnitude of that is 100 Newton meter. Another example, this simple example, so let's add another part to that. So I go ahead and again, the same thing here. So assume I have, so it goes up and goes 1 meter here, and then it comes back down for 1 meter. Assume this is the point O, so that's 2 meter, and this one is 1 meter, and this is also 1 meter. And this time I apply the force here, so I apply 100 Newton here. To find the moment about that, the very first thing, again, choose the positive rotation direction, which is, as here, choose the counterclockwise rotation as positive. So the M about O is going to be, so is it positive or negative? Again, I assume I connect the rope from the O to the force, connect to the, and let that fixed at the O, and see which direction the force is going to rotate that rope. So I have a rope connected from O to the force, and let it to rotate it. So that forces tend to rotate it this direction. So if I bring the rope here, fix it here, apply the force like that, it bring it in this direction. So it's going to be counterclockwise. Because of that, it's going to be positive. The magnitude of the force is 100. And then we need to find the distance. Again, if I connect the O to force directly, it's not going to be the normal distance. I need a normal distance. That is not going to be normal. If I connect it from here to here, there's going to be some angle here which is not normal. It's not 90 degrees. In this case, again, as I said, we extend the line of action of the force. So there's the line of action of the force, and then we draw the distance from, we draw the normal distance from the point to the line of action. So this is going to be D. In this case, D is 2 meter, is 2 meter here minus 1 meter, so it's going to be 1 meter. And again, so the distance is 1 meter, so this time is 200 Newton, 200 Newton meter. Sorry, 100 Newton meter. So it's going to be 100 Newton meter. So it's a positive, means it's counterclockwise, and its magnitude is 100 Newton meter. So these are simple examples show how we can look at the we can look at the object and see which direction it rotates, and then find the distance to the force and calculate the moment about any given point that we have. Okay, let's look at a little bit more complicated example and see how we can find the moment about any given point. So assume we have a shape like that, so it goes 3 meter up, and then with the 30 degree angle extended to that direction, and want to find the resultant moment about the point O. See, we have 20 Newton force here, and then we have 10 Newton here, and then we have 5 Newton here. So we have 3 forces, and want to see what's the moment about the point O. So when we deal with this kind of situation in 2D, probably the best way we can solve the moment problem is that if we have a force that is not in the x and y direction, find its component in the x and y direction. So very first thing probably better to do is that if we are dealing with 2D, go and find all the force component along the x and y direction before you start to find the moment. So in this case, here, if I look at that force here, if it is a 30 degrees, then that's going to be also 30 degree. So if it's a 30 degree, this is a 30 degree. So then I have a y component here, which is going to be 5 cosine 30 degrees. And then on this direction, I have also, on x direction, I have its component that is going to be 5 sine 30. So I have the y component, I have the x component and y component of that 5 Newton force. So the very first step, find all the forces in the x and y direction. So the 20 Newton is the x direction, the 10 Newton is the y direction, and the 5 Newton, we find it in the x and y direction. After that, we are going to start to find a moment about point O. The first thing, again, define the positive direction, and then we're going to find all the moment about the point O. The positive direction, as I said before, I consider counterclockwise to be positive, and then I'm going to start to write forces one by one. So let's start to write it from the start from the 20 Newton here. So if I go from that 20 Newton here, okay, I write it here. So it's positive sigma m says for the very first is the 20 Newton. So is it rotated clockwise or counterclockwise? Again, if I connect the rope from here to that force and see which direction is going to rotate that rope, is going to rotate that rope this direction. So it's going to be clockwise. So because of that, it is negative, because the clockwise and it shows counterclockwise to be positive. So the negative, the F is 20, and the distance is here, the normal distance in this case is, if we look at the normal distance, in this case we can find the normal distance like this, so it goes like this. So it's a normal distance, and because of that it's 2 meters, so it's times 2. Then I go to the 10 to see if it's a what's the moment it creates. So look at the 10 Newton. The 10 Newton passed through the point O. Because it passed through the point O, if I extend the line of action for that 10 Newton, if I extend it, the line of action for that 10 Newton, it goes right into point O. So the distance between point O and the line of action of that force is 0. If I extend the line of action goes through point O. So the distance, the normal distance between the point O and the line of action of the force is 0. In other words, it doesn't create any rotation, and it's the same as here. Again, if I hold my marker like that, if I apply the force like this, it doesn't make any rotation. To make a rotation, my force should not go through that hinge. If I put it like that, it rotates, but if I put it like that, it doesn't matter how much I push it, it's not going to rotate, because the force goes through the that hinge or the point we are calculating. The same here, because 10 Newton goes through the point O, is not going to create any moment. So it's going to, I just write it to here, but it's not going to do anything. So it's a 10 times 0. So it's the magnitude of force, and the distance is 0. So it's not going to do anything. And now I come here and look at these two forces. Let's look at first at the horizontal force is 5 sine 30 degrees. If I see if it rotates clockwise or counterclockwise, again, I connect the rope from point O to that force and see which direction is going to rotate that rope, and it's going to rotate it this direction, which is going to be the counterclockwise. So it's a positive. And then it's a positive, so it's going to be counterclockwise, and the magnitude of the force is 5 sine 30. And then the distance from here to there, what we want is the distance should be go from here, because if you connect the point O to the force, it's not going to be the normal distance. We need the normal distance. To find the normal distance, we are going to extend the line of action for that force. So we extend the line of action, for that force, and then we find the distance from the point O to that line of action. So if I clean this, so the distance from the normal distance from here to this is going to be the normal distance from point O to that line of action of the force 5 sine 30. So that distance, to find that distance, we know this part of that is the 3 meter. So this is 3 meter, and then we need this length as well, which this if you want to look at this length, is going to be well, what we have here. So to find that distance, sorry, it's not 1.5, this is 1.5, so that distance is 1.5. So if you look at that distance, what's the vertical distance going to be? 1.5 sine 30. So this is the distance that we have there. So in total, the distance is the 3 plus 1.5 sine 30. So it's going to be the distance here. So 5 sine 30 times the distance, which is going to be 3 plus 1.5 sine 30. So that's the distance. You can find it from these triangles. I draw that triangle here again. So it's 30 degrees. This is 1.5, and this distance is going to be 1.5 sine 30, which is what we have it here. Then the last force we have is the 5 cosine 30. Again, we look at if we connect the rope from here, from the point O to that force, and look at which direction it's going to rotate. Again, it's going to rotate it counterclockwise. So look at that, it's going to make the rope rotate that way. So again, this is positive. So it's a 5 cosine 30. And the distance, we need the distance from there. So we cannot, again, find it. We cannot connect from point O to the force. It's not the normal distance. We need the normal distance. To find the normal distance, we extend the line of action for that force. And if I extend the line of action from that force, this is going to be the distance I need. This is going to be the distance. And this distance here is, so look at that, it's going to be 1.5 cosine 30. Again, in this, if you look at this triangle, the triangle here, I just draw it here, the triangle here, 30, and this length is 1.5. So this length is going to be 1.5 and cosine 30, which is going to be this length. So that's the distance here. It's going to be the force times 1.5 cosine 30, which is going to be distance, and then we can add them all together, and it comes out 25 Newton meter eventually if we add all of them together. So remember, these are the force. So this is the distance, this is the distance, so this is distance, this is distance, and the other part are forces. So so this is force, the 10 is force, this is force, and this is force. So what we have done, in other words, to calculate that sigma m but O, to find the resultant moment from O, we add all the moment, all the F times D, and add them together based on if they are clockwise or counterclockwise. Add them all together, and eventually we get this value, negative 25, which is, it shows that it is going to be clockwise, and its value is 25 Newton, so its value is 25 Newton meter.